Hello students, next we are going to look into the signal transmission through linear system, which is the third module, first part. There are two parts. First is the signal transmission through linear system. The second part is on sampling. So let us start with the signal transmission through linear system. When we are talking of a system, we have already seen what is an LTI system. LTI system. LTI system basically stands for linear time invariant system. So the LTI comes from linear time invariant. That is the LTI system. There are other systems also which are basically called as linear time variant system. This is called as linear time variant system. In linear time variant system, what we are having is that how it is different from LTI system is that the system changes with time. So you should understand what is the meaning of linear. In the case of linear, we say a system is linear if it obeys the superposition rule, or what we used to call as the homogeneity rule. If you remember, the homogeneity rule will basically make the system a linear one. That means if we check if the system is homogeneous, it means that the system is linear. Okay. Then what is time invariant? Time invariant is something that changes with respect to time. Variant is something that does not change with respect to time. A system that does not change with respect to time. Whereas time variant is something that is changing with respect to time. Okay. For example, if you take a radio system, in a radio, a signal is coming from very far away and it is reaching the radio antenna, and every time the signal is not having the same strength. Sometimes the signal strength goes down, isn't it? So it is a time variant system. The system is varying with respect to time. Whereas in some cases, it is a time invariant system. Mostly we will start with time invariant system as you go into higher semesters, or as you go into problems that are more and more complex, you will come to time variant system and also into non-linear systems. Okay, so non-linear time variant systems are also there, but anyway we will discuss only linear time variant systems. So how do we define the linear time variant system? Time invariant system is, if you remember, we had written an equation some time back which was y of t. That means the output of the system when the time is delayed by t is same as the output delayed by t. The output of the system, so this is the system output. The output of the system delayed by t is same as the output itself delayed by t. Then it's a time invariant system. And if we are having y t comma t, that means the system is delayed by t and its output is not as the output itself being delayed by t, then that is a time variant system. You can go to our previous classes, there we have done even problems based on this. Okay, so we will look into some of the properties of LTI system. So properties of LTI system. Properties of LTI system. So one of the properties of LTI system is commutative property. The commutative property basically says that x of t convolution with h of t is same as h of t being convoluted with x of t. So what is the meaning of that? It means that if you are having two systems, if you have one system with, with the system being h of t and the output and the input being x of t, we know that the output y of t is going to be the convolution of x of t with h of t, or even h of t with convolution with x of t. So this is the commutative property. That means if an input is coming x of t to a system h of t, then the output can be given by either the convolution of x of t with h of t or h of t with x of t. This is something that we have already proved for the case of convolution integral. Okay. Now similarly for the case of discrete time, it will come as x of n, h of n. That we will see when we reach there. Anyway, the second property that we are having is the distributive property. The distributive property basically takes into consideration two systems. So suppose if I am having a system which is h1 of t and another system which is h2 of t, then the combined effect of that system, convolution with x of t, will give me a distributive phenomenon. That means x of t h1 of t convolution plus x of t h2 of t, the convolution between them. So what is the physical meaning of this? The physical meaning basically comes from here, that suppose if you are having two systems, one is h1 of t, another is h2 of t, and you are going to give both of them the same input, which is x of t. If suppose you are going to give the same input x of t to them, then the output of that, if you would add them up, you will get an output. Okay, that output is, let's say, y of t. So this is this equation. So you have given individually a signal x of t to h1 of t as well as h2 of t, and based on that you are going to have an output y of t, and that is going to be equal to the system where the output where h1 of t and h2 of t is taken as a single system, and you give an input x of t, then you get an output y of t. So what they are saying is, if you are having two systems in parallel, it's as good as adding those systems together. You will get the same output. So it does not matter, whatever be the system, if they are an LTI system, if both of them are in parallel, you can basically add them up. So instead of doing this procedure, you can basically add the systems together and then finally get the output. This is the second property. The third property is the associative property, which basically says that if you are having x of t convolution with h1 of t convolution with h2 of t, it is same as x of t convolution with h1 of t convolution with h2 of t. Now you might be asking, like, both the equations are same. No, I am saying about the associative property, so I am trying to associate one with the other. Okay, so if you first solve this bracket and then do the convolution with x of t, it is same as first doing the convolution between these two and then trying to convolute with h of t. Okay, so what is the physical meaning of that? Suppose you are having two systems in cascade. That means this is the first system and this is the second system. So the first system we are writing h1 of t, the second system we are writing h2 of t, and you are going to have an input. Okay, from the first system the output travels to the second input of the second system, and then you get an output. Let that output be y of t. So this is your x of t. Okay, this scenario, which is basically represented by this equation, this equation, this is the output of the first system, which is the input of the second system, and then that is convoluted with h2 of t to get the total output, that is y of t, which is basically the whole convolution together. Okay, so this is the right hand side equation diagram that I have drawn. Now this is going to be equivalent to the case where you are having a single system representing the cascaded effect of both the systems. So if two systems are cascaded, then it is as good as you write or you find out the convolution of both the systems together. That means h1 of t convoluted with h2 of t, and if you give an input x of t, you will get an output y of t, and both these are going to be equal. Okay, so either you do it in this way or you do it in this way. So this is basically represented by this equation. So what is the use of this? The use of this is, if two systems are in cascade, you can represent them by a single system by considering them the system to be a convolution integral of both the systems. Okay, so this is how you represent a single system which are in cascade. That means convolute both of them. If they are in parallel, as we have done previously, then you basically add them up. Now we are going to come to the final place or the final understanding of the system and the signal for any of the future analysis. This is very important for you to understand, because whatever you are going to do in future in signals, in systems, is basically based on this understanding of the system. So you have to be very focused in this particular section. It's nothing difficult, it's only an understanding of what is happening in the system. See, whenever we are talking about a system, okay, whenever we are talking about a system will basically consist of, so I will write here system. A system will basically be represented by either the time domain h of t, or the frequency domain h of omega, or the Laplace domain h of s. Okay, this is the time domain. The second one is the frequency domain, and the third one is the S domain, or what we call it as the stability domain. Okay, S stands for stability. And you are going to give a signal at the input, and the signal at the input we generally represent it as x of t, and the output is y of t. Now what is important to understand is that you can get the output of the system y of t by taking x of t and convoluting it with h of t. That is one of the methods. So one method. Okay, this is let me say that this is the first method of solving. This is the first method of finding out what is the output when you have a system. Or the other method that you can have is, if you know the system and you know the signal, you find out what is the frequency domain of the signal, that is x of omega. Okay, you find x of omega and you get y of t by the following step. You first multiply x of omega with h of omega. So it is multiplication, mind you, and you will get the output as y of omega, and then you try to find out what is the Fourier inverse, what is the Fourier transform inverse. So this is the second step, will be to find out the Fourier transform inverse. So you know that Fourier transform inverse is basically written as f inverse of y omega, and you get back y of t. So this is the second method of finding out. This is the second method of finding out the output of a system when you know the input and the system. And the third, as you might have guessed, you find out the Laplace transform of the input signal. So I will write the Laplace transform. I forgot one thing, I should not write this as small x, I should write it as capital X. Okay, so this is also capital X. In this way, this should be written as a multiplication, a small multiplication. Okay. Okay, so the next method, the third method, is you find out s, and then you basically find out y of t by multiplying x of s, not convolution, only multiplication. Okay, multiplying with h of s, you get what is y of s, and then you take the Laplace inverse of y of s to obtain what is y of t. And this is the third method. Now you might be asking, why should we go for all these when we can do it simply by the first method? See, the first method is convolution, and you know that in certain cases the convolution turns out to be very, very complex. You have done convolution and you know that you have to do a lot of integration and all those things. But when you do the Fourier transform of that, it becomes a simple algebraic equation. Or if you take the Laplace transform of that, it becomes a simple algebraic equation. So what it tries to do is, it converts it transforms, the Fourier transform transforms the signal into frequency domain, and then it becomes a simple multiplication and finding out the Fourier inverse. Whereas in the first method, it is quite difficult in certain problems, not in all problems, but in certain problems. So generally this is how this is carried out. Or you can view this in another way. You can find out, we can find h of t from y of t and x of t. That means if you want to find out what is the system, one way to do it in time domain is basically put x of t is equal to delta t, then y of t is going to be equal to h of t. This is something that you have already seen. That means if your input is an impulse function, then the output is the system itself. This is something that we have already seen. Okay, but suppose if you are having a different input and an output, then how do you find h of t? Now generally people will say that, okay, we will just do, since x of t convolution with h of t is going to give us y of t, we can find out y of t by simply, we can find out h of t by simply dividing y of t with x of t. No, that is wrong. This method is wrong, because here it is convolution, it is not multiplication. If it is multiplication, you can do that, and that is where the advantage of Fourier transform and Laplace transform comes. So we know that x of t convolution with h of t will give me y of t. The Fourier transform of that is going to be x of omega multiplied with h of omega. What is this? You remember the convolution property. That means convolution in time domain leads to multiplication in frequency domain. The property that we had studied in the Fourier series and Fourier transform. So based on that property, the convolution that is happening in the time domain, we are changing to multiplication in the frequency domain. Then you can find out h of omega to be simply y of omega divided by x of omega, and you can find h of t by taking the Fourier inverse of h of omega. The same case is true with Laplace. Okay, in the case of Laplace, you will convert x of t into x of s, again multiply with capital H of s, and then you will get the output y of s. Therefore then you can find out h of s by simply dividing the output, that means the Laplace of the output y of s, with x of s, and then you get h of t by simply taking the Laplace inverse of h of s. So one of the ways to find out the system with the help of input and output, so how can you find out h of t from x of t and y of t? It is not by dividing them, but actually taking the Laplace or Fourier transform of them, and then using this formula, that means output divided by input, you get whatever is the system in frequency domain. Then you find out the Fourier inverse of that to find out what is the Laplace domain. Let me write this properly. To find out what is the time domain of the things. Another important thing that we have to remember is that if you have already a function h of s, you can find out the system Fourier transform h of omega by substituting s is equal to j omega in the equation of h of s. To take from Laplace domain to Fourier domain, all you need to do is substitute the value of s with j omega. So if there is s square, you take j omega the whole square, which is actually j square, which is minus, and omega square is omega square itself. So like that, this is also a very good thing that you have when you have the transform. You can go from one transform to another transform. So these are all tricks that people use when they use the Laplace of the Fourier transform. Let us solve a problem to elucidate this particular concept. So consider a stable Lti system which is defined by this particular equation, and find h of t. So as I said, this equation is a normal differential equation of y of t and x of t. They will sometimes they will also give the initial conditions with this, but in this particular example that I have taken from one of the textbooks, they have not given the initial condition, so I will neglect the initial condition while solving. So let us see how do we solve this. Okay, so first thing is we will take the given equation. So the given equation is d by dt of y of t plus 2 times y of t is equal to x of t. Okay, taking Laplace transform of this above equation, we know that the Laplace transform of a differential equation of any function is d by dt of y of t, d by dt of y of t, the Laplace transform is going to be s y of s minus y0. This is small y0. Remember this. Okay, this is small y0. This is something that we have already done in network theory. This is small y0. Small y0 is basically in time domain. This is in the Laplace domain. This is the initial condition. If you remember, y of 0 is the initial condition. Okay, and then similarly 2y of t, if I am going to take the Laplace transform, so I will write here Laplace transform. The Laplace transform is going to be 2y of s. Therefore, the equation is now s y of s minus small y0 plus 2y of s, and on the right hand side x of t, taking the Laplace transform, we will get capital X of s. Now y of 0, it is not given, so I will write neglecting the initial conditions, that means I will write that y of 0 is equal to 0. I am just, because it's not given, so I will take it as 0. So whatever remains is s y of s plus 2y of s is equal to x of s, which basically, this is x of s, yeah, which basically becomes s plus 2 y of s is equal to x of s, or I can write y of s by x of s is going to be 1 by s plus 2, and this is going to be, as you have already studied just now, that y of s divided by x of s is going to be h of s. Therefore, if you want to find h of t, it is the Laplace inverse of h of s, which is the Laplace inverse of 1 divided by s plus 2. Okay, and if you remember, we know that 1 by s plus a, the Laplace transform or the Laplace inverse transform of that, is going to be e raised to power minus at u of t. You remember this? Okay, so we know from the Laplace transform, that the Laplace inverse of 1 by s plus a is going to be equal to e raised to power minus at into u of t. Therefore h of t will be equal to Laplace inverse of 1 divided by s plus 2, which is e raised to power minus 2t u of t. So we have found out the impulse function directly from this equation without solving the differential equation. By simply taking the Laplace transform, I have transformed that differential equation into an algebraic equation, and from that algebraic equation, by using the Laplace inverse transform, I have found out the answer of what is the impulse response of the system. So this is what I said, mathematically, if you want to solve very complex equations, it has become very easy, because you can transform it into Laplace transform, solve the system, and finally again convert it back into time domain to get this particular answer. Thank you.